All right, we're now going to return to calculus. And this time we're going to look at the integration. Last time we visited calculus, it was differentiation and the rules for that. So integration is the reverse operation. But just like we did when we introduced differentiation, we originally introduced it to solve a problem. Remember, how do we find the equation of a tangent? And that's how we're going to introduce integration as well. We're going to solve a problem. How do we find the area underneath a curve if it's not a regular shape? If there were straight edges, not a problem. We could use area of a triangle, square, rectangle, whatever the shape happened to be, trapezium for that matter. But when it's a curve, and it's not a circle, we've got a formula for circle, how do we find this area? So this is y equals x cubed. Best we can do, I guess, is estimate. Now this is a pretty lousy one, of course. I'm estimating with a couple of rectangles. And clearly, my estimate with these two rectangles is too big because I've got all these gaps above the curve. But I know then that the area under the curve is going to be less than the area of those two rectangles. Okay, and the first rectangle has a height of 1 and a width of 1, so 1 times 1 cubed, because the function's x cubed. The second rectangle would have a height of 2 cubed and also a width of 1. So I know it's going to be less than, well, theoretically it could be equal to 9, but we know it's not because we can see from our picture. But then I could draw a couple of smaller rectangles which actually go below. Well, the first rectangle actually is just a straight line with a height of 0, so the area under the curve would be more than the blue rectangles. So the blue rectangles would have I'd say the first one, height of 0 cubed, it's a straight line. The second one has the height of 1 cubed and the width of 1. So I know the area is certainly going to be bigger than 1. Just as a lousy estimate. It's somewhere between 1 and 9. I mean, it's quite a wide range. I suppose if I wanted to, I'd average them and I could say, okay, my estimate would be 5. It actually turns out to be 4. So that tells us how bad our actual estimate is doing this. Okay. Well, I use 2 rectangles. If I use more rectangles, then I'm going to have less space above. So if I use now 5 rectangles, I've reduced the amount of oversize. These are what we call the outer rectangles, by the way. We call them the outer ones because there's area outside that we don't want. And the blue ones would be the inner rectangles, so it's all inside the actual area. The area for these ones, I've now made the width 0.4, so the different heights will be 0.4 cubed, 0.8 cubed, 1.2 cubed, and so on. And that's 5.76. So it's reduced the area quite considerably. Remember, it was 9 when we did it before. We've now got it to 5.76. And I could do the inner rectangles as well. And they also have a width of 0.4. The first one, though, is a straight line. It's 0 cubed and 0.4 cubed and so on. 2.56. And if I average those two out, it's getting better. 4.16. Remember, the exact value we said was 4. So that was with 5 rectangles. What about if I did it with 10 rectangles? There we go. There's the 10th one. So the width would now be 0.2. And the first one, 0.2 cubed, 0.4 cubed, and so on and so on. That actually turns out to be 4.84. And the inner ones, so let's draw those ones in, the little blue ones. There we go. So 0 cubed, 0.2 cubed, and so on. That turns out to be 3.24. 4.04 with 10 rectangles. So we're getting a lot closer. So you can see, the more rectangles we have, the better the estimate's going to be. So ideally, how many rectangles would I like? Yeah, if it was possible, I'd like to draw an infinite number of rectangles. The width would be getting very close to 0. This is where we're going to use limits. We say we want the width as it approaches 0. And we'll come up with an exact value. So this is now just a random curve, not the y equals x cubed. Let's have a look at that idea, see if we can come up with a formula which will work this out for us. So there's one of our supposed rectangles that I've marked in blue there. Now, obviously, the top's not straight at the moment, but remember, we're going to end up saying the width is close to 0. So it would end up being pretty close to straight. I'm going to define this function. It's the area function. If I can find the area, a function that works out area, then all I've got to do is substitute into that function and I can calculate the area. So A is standing for this area function that I'm trying to find. And it'll work out the area from 0 to C. Area X then would be the area from 0 to X. So the area of the rectangle would be the difference between the two. So my rectangle will have an area of area X minus area C. And let's say we can estimate that with a rectangle. The height will be function X, or function C for that matter, because we're assuming they're so close together they may as well be the same thing. But we'll say function X. So the area of my rectangle will be very close to X minus C times function X. If I play around with that, I can say, well, function X is area X minus area C over X minus C. Well, instead of calling it X, I'm going to call it C plus H. Don't ask me why I didn't use W, okay? I'm using H for width of rectangle. So instead of saying X, I'm going to say C plus H. So I have area of C plus H minus area C over H. The real reason I used H is hopefully this is starting to look familiar. So as the width of the rectangle decreases, our estimate is going to become more and more accurate. So if I use limits, if I say as H approaches 0, that area is going to become exact. We'll have an infinite number of rectangles, if you like. So I'm saying it's exactly going to be the limit as H approaches 0 of this area function when I sub in C plus H minus when I sub in C all over H. But of course, if H is approaching 0, C and X are approaching to be the same thing. So I'll just replace the C with an X. And now again, hopefully this is starting to look familiar. Limit as H approaches 0 of this function X plus H minus this function X over H. Well, that was our formula for the derivative. Our first principles formula we came up with. So in fact, what we now know is the actual equation of the curve is the derivative of this area function we're trying to find. So if we know the equation of the curve, we can work out the formula for the area. We just have to say, well, what did I differentiate to get this equation? That's what we call the primitive function, if you remember. So the equation of the curve is the derivative of the area function. So if I want to find the area underneath a curve between x equals a and x equals b, the symbol we use is the long S symbol. That's the symbol for integral, a long S. Stands for sum, because basically you're summing up the areas of all these rectangles. Okay. We place the limits a to b, where we're going from, and then the curve that it is that we're finding the area underneath, or integrating. The answer will be this new function, the area function. I'll substitute in the area up to b, subtract the area up to a, and that will give me the area between a and b. And function x, this new function, this area function, is in fact what we called the primitive function. So let's go and see how I worked out the exact area was indeed 4. There's the question that we did. Y equals x cubed, and we did it between 0 and 2. So I can now say, well, that area is the integral of x cubed with respect to x. So just like in the derivative, we wrote dy dx, we said differentiate y with respect to x. In this case, I'm integrating with respect to x. So the dx is saying with respect to x. And I'm going from 0 to 2. When we're finding the primitive function of just a polynomial, remember it was add 1 to the power, because it's the reverse of differentiation. When we differentiated, we subtracted 1 from the power. And the other difference was, instead of multiplying by the power, we divided by the new power. So this one will become a quarter x to the power of 4. Add 1 to the power, it becomes 4. Divide by that new power. And we're going to substitute in 2 and 0. So I can always factorise the quarter outside the brackets. You can always factorise constants, just not pronumerals in this sort of thing. So a quarter, 2 to the power of 4 minus 0 to the power of 4, 4 units squared. And that's how we worked out the exact value. So I get a question like this then. Now, if they don't say find the area, and they just give a question like this, it's no longer an area question. It's simply, oh, find this value. Area is just an application of integration. So I'll put units on it if they're saying find the area. If it's just an integral like this, I'm not going to put units on it. It might represent something else. And as we go through the course, we'll see other things that integrals can represent. Add 1 to the power over the power. X squared then will go to 1/3 x cubed. Our constant 1 will go to x, or I guess you could think of it as that is x to the power of 0. So add 1 to the power, you get 1 over the power 1. Substitute in 3 minus substitute in 2, and we get 22 on 3. As I say, that's just a value. There are no units attached to this particular question. Negative indices work just as well. Just be careful because you're adding to a negative. Temptation is to go minus 4, but we're adding, we go to minus 2. So it'll become minus a half x to the minus 2. I've converted it out of index form, so I've said, oh, well, that'd be 1 on 5 squared minus 1 on 4 squared. So we end up with 9 on 800. Okay, so let's have a go at just a handful of those. See how we